So I guess we can get started. So welcome everyone to our quarterly community meetup. Happy to see all of you here. So maybe some of you're here for the first time. So this is a meetup where we sometimes we invite our users from the community to do a show and tell. And sometimes we have specific topic regarding QuestDB. But after all, we are trying to have including more interesting topic in the future, and we're welcoming all kinds of suggestions for any future meetups that we have. And as for today, we're gonna have a very short updates about QuestDB. And we're going to have a community show and tell from one of our users, Holger. He's working at TQS integration. And then my colleague, Andre, he will be talking about InfluxDB protocol. It's specific about performance optimization. And at the end, if we have more time, we can have some chats and discussion to cover whatever you want to cover. Yeah. So some of the recent updates about QuestDB, we released 6.2.1. So if you haven't updated to it, there are several bug fixes. So we will definitely recommend to upgrade. And the next release will be 6.3, which contains the update function that many users are looking forward to. There are also new case studies recently published with the TQS integration, Sapient Industries, and live action, and you can find them on our website in the customer page. And on next month, on April 26th, Vlad, our CTO, will be speaking at a CMU database talk. So welcome to join. So I'm gonna hand over to Holger, if you're ready.
Okay, let me just share my screen. Can you all see it?
Yep. Yes.
Yep.
Very cool.
Yep.
Yeah, perfect. So I will go over a couple of slides, not a lot. So it's not going to be a PowerPoint presentation. I mean, I will just set it up and then we can look at some live data and see how it looks like. And just a brief introduction about me. So I'm originally from Germany. That's where I got my accent from. Now I live in Tallahassee, Florida. And originally I was a chemist, but I gave that up like 10 years ago and went into consulting, and this is in data architecture and infrastructure consulting. So the last 4 years, I worked at TQS integration, and this is a system integration companies. Our clients are all over the world now. We started with 2 people in 2000, Maura and Tom Quilty, who founded the company. And then we grew over time to over 200. And last year we were acquired by Cognizant as in their biotechnology division. And the primary focus of our industry is basically to provide data access for manufacturing companies, real-time data, sensor data. And this is primarily our focus, I mean, in this company. So I think a lot of people that use QuestDB, they're using it in the financial industry. I mean, in manufacturing, we also had time series databases, and that for a long time. So you can say for over 20 years, I mean, manufacturing data are captured in time series. They just have a different name. They're called data historian there. So for real-time data, people can actually look at the HMIs and the screens, and for historical data, they would actually look into a time series database, or as I mentioned, data historian. Just to explain a little bit about the industry, I mean, when you talk about the data historian in manufacturing, it's not a single component. I mean, so I know that QuestDB is singly focused on time series data, But in manufacturing, that's a little bit different. And that has something to do with technology stack. So yes, there is a database that captures time series data. And most notably, I mean, they're storing data as snapshot data, which is the current data stream. And then they actually archive some of the data. So they're not archiving all of the data, but in most cases, the data is then compressed to only the significant events in this data stream. So we have two different data sources, and I will talk a little bit about that later. So you have like the snapshot data very, very fast, and then you have the archive data, which are compressed by lossy data compression algorithm. The benefit of that is that these databases that have been around for a long time, they have a very, very small footprint. I mean, due to the compression algorithm, I mean, so it's not a CPU hog, or you don't need a lot of memory or disk space. I mean, they're very moderate in the consumption of your resources. But then the other thing, and this is even more important in manufacturing, is in this technology stack, I mean, these vendors also provide the interfaces to the manufacturing environment. And this is basically where the technology is. So you have people that these companies basically focus on getting the automation data, which is also proprietary, into the time series database. So they provide you with interfaces, connectors, and adapters for all types of different vendors and automation systems. And lately, they have also included metadatabases, and I will talk about that also a little bit later, is to provide an abstraction layer or an analytic layer, I mean, for your time series data. So you have context to your data. And of course, then out of the box, they provide you with client tools to work with Excel or create a dashboard or create reporting. So a time series database, I mean, a manufacturing called data historian, is really a technology stack, and you basically buy the whole package of a proprietary system, basically. Does that make sense so far?
So far, so good.
So far, so good, okay. So the interesting part about manufacturing data is, that you have different types and shapes, So of course you have your sensor time series data, which is an infinite stream of timestamp values. I mean, so this is the time series component of that. But then in order to make sense of the data, you also need a time model and a physical model. So the time model is basically the slices of your process in time with a start and end time. And then the physical model is basically where that sensor is actually located. How does it fit in the plan? And these are basically pretty extensive models, I mean, that are put in place to describe how the manufacturing plant is actually structured. So when you look at your home, for example, you're looking at a temperature sensor that records the temperature. Then the time segment would be, for example, if you want to bake a pizza, what stage in the process you're in. Are you doing the dough? Are you putting it in the refrigerator? Are you baking it in an oven? That actually, that actually gives it context. The temperature measurement when you're in the oven, when you're making the dough, is of course meaningless for the process. You only need it when you actually put the pizza in. And then, of course, the physical model is where's that temperature sensor located. So it doesn't make sense when you bake the pizza to look at your thermostat. That's still like room temperature. That doesn't give you any information about the quality of your product. So context in manufacturing is pretty much everything. So once we looked into that, I mean, and also into QuestDB, there are a couple of other things, that we struggled with in the past, that we also now started to work and also starting to look for time series databases that allow us basically to come up with a flexible schema for complex processes. So one very, very common topic is alarm and events. How do you store alarm and events? And to understand alarms, you have to understand this is kind of like a life cycle. There's an alarm going off, then some operator has to acknowledge it, and then at some point when the alarm is basically cleared, then that segment actually closes. So it has different steps and of course different metadata assigned to it as well. So these are kind of like SQL type data, but they also have a time series component to it. They have a timestamp, when these events happen. So we had a hard time structuring the data in the past because data storing and manufacturing, I mean, usually only has the primitive data types, let's say string, int, bool, and floats. And so you're a little bit limited in what you can do in terms of like modeling these data. And the next one is the one below. These are sensor and online analytics. This is also a time series. So a lot of our clients now basically record very complex information during the process. It's called online monitoring. And what it does, it doesn't give you a single data point. It just gives you a spectrum. So at each point in time, you have a timestamp, then you have channels of your measurements, and then the value of, what this metric is actually giving you. So they can, with one shot, they can measure 4 or 5 different components in your process. So it's very, very powerful, but of course also provides a challenge for us, to basically store the data and then also display them in the context of your other manufacturing data. So schema really important here. And then the last one, and I think this will come more and more, is multivariate analysis and machine learning. These are very popular in our industry. We work mostly with biotech and pharmaceutical clients, so this is a large customer base of us. And they use multivariate models. And these models, have 2 components. One, of course, is a prediction. The other component is basically what they call explainer. And this is really important for manufacturing. So yes, it's important to know where the temperature is 10 minutes from now, but in manufacturing is also equally important what causes the temperature to rise to a certain level. And these explainer come in a form from machine learning in terms of vectors, matrices, and tensors that you also need to store ahead of time, or during the runtime. So people, when they actually do the dashboard, can actually look at each point in time and get the explainability for that point from your machine learning model. The whole thing is called digital clones in the industry. So you want to basically clone your physical machine or your process into like a digital way of it, but that basically includes that you also give people an explanation of how does the model come up with that type of value. They also have to be stored. These are also time series data, but of course, they have a different shape, than your typical primitive types. Any questions to that part? All good? All right. Here's just to give you a flavor, how that all looks. One equipment in the plant, you can see all the different metadata of the physical model, the SAP ID, that's like your enterprise resource planning tool. Then, where it's located, description, location, coordinates, and size, of course. And then you have your time model, also included in this metadata base. And then, of course, your time series data, which are the critical parameter like dissolved oxygen, internal temperature. This is for the autoclave, and so on and so on. And also here, as you see, it's described before, you have alarm message, an event message, and auto messages. These are basically the SQL type data that also have a time series component, and where we're also looking for solutions to store them in scale. Just as a side note, I was in one plant and somebody told me that they have tens of thousands of alarm messages per day. So it's really also from the volume, a thing that is actually causing some trouble. Okay. So I now describe a little bit about 2 use cases I think that are interesting where we actually use QuestDB. So the first one is at the very beginning of the presentation, I mentioned that the data historian have 2 types of data, the raw data and then the compressed data. And the way they reduce the number of data is by a compression algorithm. So we call that hot data stream and cold data stream. The cold are the compressed data, the hot are the raw data. And the compression actually removes some of the data from the stream and only stores the significant values in the database. And that in manufacturing often works really, really well because the movement of these process variables is often very, very slow in time. So you don't really need to record every single data point, for some of these slow moving processes. Just to give you an idea, in modeling, in biotechnology, they need data points every 15 minutes. So it's a long stretch of time, before you actually need a brand new data point. But of course, there are other processes that can benefit from faster data acquisition. And for that use case where you actually want to have a higher resolution, we, instead of like this table or this queue, we remove that and put a QuestDB database in there. Because the perfect fit, these are high frequency data, a lot of load. Some of these plants, they have 50 to 100,000 process variables. So you have a lot of information that goes in, sometimes sub-seconds updates. So it's a perfect use case for QuestDB. As a buffer day, basically, if the buffer database, a short-term database for high frequency data. You don't need to store them for a long time because, for longer time calculations, I think it would be still a good idea to compress them into like a cold data store. If you're looking, for example, months or years worth of data, of course, a lower data rate is, of course, beneficial. But for a shorter time frame where you look at fast moving processes, this is a perfect fit for this. And now it gets a little bit more complex. Of course, to expand on that is a lot of our clients looking at cloud architecture. So what they want to do is, they want to use a data historian, and then they want to move the data into the cloud. And to do that, we have an MQTT interface that serializes these data from the local data manufacturing network and push them through a broker into the cloud. And this is basically in the demo. This is not going to be the cloud. This is just a regular container, a couple of containers that are set up for the demo. But the whole workflow is basically identical. So you first have to serialize the data, and then you have to get them through an event hub, and you can do streaming analysis, and then you can also set up your 2 data stores. And here we also have cold and hot data stores for the compressed and raw data. And when we started that, because we have a lot of clients that are interested in this type of solutions. We looked a little bit at what are the requirements, what are the specifications for a solution like that. And so from a raw data stream, we estimate that this will be 100,000 events per second. And this is based on the calculation of 50 to 100,000 process variables that are updating every half a second. Then, of course, we have data compression. And the industry we're working in, the data compression has to be identical on-premise as it is in the cloud. This is just for validation purposes. They're looking at identical points, on both source and destination. Then, of course, you need to have minimal and known latency, and I will talk about that also a little bit later. And then, of course, data quality, integrity, and availability. These are all terms, in manufacturing that describes, the properties of your data that are going into the cloud. Any questions to that part? Good. Fine. So the second demo that I show, and I just go through them, so we can then look at the real thing, is as I mentioned before, in manufacturing you have 3 components: the time series, the time model, and the data model, the physical model. And the question is, of course, when you serialize them to the cloud, you basically have to recreate these type of structures to make meaning for operators, when they look at it. So as I mentioned before, if you bake a pizza, you want to know what state you're in your recipe, and also want to know where the temperature is actually recorded. And that is basically what we demonstrate in that example. So here we have the recipe data as a time model, and the physical model as, let's say, a bioreactor. And this is, of course, all simulated right now. Okay, so let's look at the first one. So again, we have 2 different colors. We have the red data. These are your fast-moving hot data stream. And then you have the blue data, which are your compressed data stream. And I don't know if I can remove that here, but what you can see is basically you have around 1,600 hot data or high-frequency data and only 19 compressed data points. And that's basically how this algorithm works. It basically is only storing significant values in your data stream. And when you look at both curves, they look pretty close together. You see some deviations here and there, but that works pretty well. The reason why it works well is, of course, that signal, which is a sinusoid, is a very slow moving signal. It's a low frequency signal. So compression like that works pretty well. The moment you introduce noise or have faster movements, that compression ratio is, of course, going to be much, much lower. So it really depends on your signal type. So for most of our processes that range in, as I mentioned, in biotechnology, process range or in a scale of like several days, then of course this works pretty well. If you have a faster process in manufacturing, for example, filling these little vials, these filling lines for the vials, they might be in the range of sub-seconds, then of course, you would need to have the red data points, you have to have high frequency data. And then and this is where schema becomes important. So the one thing that we also wanted to do in this proof of concept is basically also to time tag, the values to see exactly what is the latency of the values when they're actually going through the system. So we measured that for every single data point. So for every single data point, you're getting the value, you're getting the information if it's a compressed or a raw data point, you're getting a quality flag, and then you also get a latency of each single data point. And then you can create these type of curves where you can see, okay, right now, the latency on premise is around 600 milliseconds. So this is basically, because it's on premise, and then, when you look at all the data we're pushing through it, you can also see it's like under a second. So for high frequency trading, you would lose a lot of money, if that's your latency. But in manufacturing, this is, of course, that is, depending on your process, a very a good value for that. So then we can actually also think about, okay, how does that then look like, when you look at analytical application? And it's pretty easy then. If you know your latency, if you have high frequency and low frequency data, you can think about slow moving processes. Yes, you can do them in a cloud. 2 seconds latency doesn't make a difference if you only need every 15 minutes a data point, a measurement. So that works pretty well. If you have data under 1 minute, you can do that in the cloud. Of course, you may have enough data, you can just use the hot data that we are providing. So if you need really, really fast measurements, then of course the whole cloud strategy has to be moved. To that, they call that edge computing. They have to be basically located on premise, where you then don't have the network latency, and you also don't need to package the data when you're sending them to the cloud. So you have a very, very fast data process and also very, very fast analytics. And here's basically the lower chart is basically how the whole system works together. There are, like, of course, different components in there. There's our Odin MQTT interface, and there's a MQTT broker, and there's a QuestDB database, and basically all the data streams for all the different systems. And we measure, exactly when they come in and what the count of them is. Also, just to get metrics about the system itself, and also to build confidence that that system actually works as designed. Any questions? No? Okay, then I go to the other one. And this has also something to do with schema. I mentioned before that manufacturing data needs both. It needs the time series data, the sensor data, but it also needs context. The context is encoded in the process variable name. You can see that up here. So this is like a bioreactor 0, and this is a path of the bioreactor. And this is not like a fully designed system, so it's a little bit a shortcut, And then this basically reflects your physical model, and then your time data model is the one below. You can see the red one is phase 1, then you have phase 2, phase 3, phase 4. These are all the process segments, and the corresponding data are aligned in time with your time series model. So with QuestDB, we are able, basically to model both, the time series data and also the data models, and serialize them to an MQTT interface, and we can show clients, how that all looks together. Any question? Was it too fast?
That was good.
Are you using I'm assuming like a beta that allows for updates in order to do the more relational data?
Oh, this is a great question. Absolutely great question. Yes, we are not using a beta, and this is basically why this schema right now is not ideal. So that is also when I would update it, you see it would be also a little bit slower, because we don't have a primary time index on this data, and because of exactly the reason that you just mentioned, because a segment starts at a certain time and then it moves forward and then it closes. So we would need to update that record to basically make it a good schema. Exactly right. And that we haven't done that here. This is just, so we're waiting also for the update where we're waiting for the update so we can update. That's basically what we're looking for. Yes, okay. And this is a lot of application also for our industry. We need to update these records, yeah.
And then the signal names, like bserver2 demo, are those mapping roughly to your MQTT topic names?
Good question too. So the way, I mean, for us to stream over 100,000 tags is basically by packaging them up. So if and so you cannot do much with the topic names because you have too many variety in your package to give it one topic name. Does that make sense? So we have so many events. I mean, we have to package them up and send them. So we cannot, so the encoding cannot happen on the topic name itself. Otherwise, we would need to send 100,000 different messages, and this is of course overloading the system. So we're packaging the data up. They go into one topic, and then they have to be disassembled, so to speak, on the destination.
Gotcha. That makes sense.
All right, perfect. And you can see it here. I mean, you can see that, there are only like 3 topics, and they're not ISA 95 encoded, or, they don't have the physical model in there. I mean, right now they're just called hot frame encode. Okay, any other questions?
So how is your physical? I'm sorry, go ahead.
Yeah,
So you're going from QTT into ILP. So what are you actually using to translate that?
So, I mean, these are all great questions. Perfect. So they're like 2 different. There are 2 different interfaces. One sits on premise as a Windows-based C# program that takes the data and sends them to MQTT, and we built that software. And then for Ingress, it's a Python module that we also built to translate what's coming in and translate it back into like the different tables.
Cool, thanks.
But of course, that the good thing now with MQTT is, and SparkPlug-B that we use to encode is, that it can be several different languages. You're not pigeonholed to one technology anymore. You can use different type of technology to read the data and translate them into the data tables.
I might have missed this, but could you explain again how your physical model or your digital twin data is stored?
Yes. So the data that are coming through here are actually coming from proprietary data historian. So the physical model is defined on premise in the plant, and we are taking that physical model, serializing it, and sending it to the cloud.
Okay, so when you query your time series, you know which fields you want ahead of time.
We check all of them.
Oh, okay.
So that was one of the questions that that was also one of the questions that we also got, and we have thought internally or had some discussions internally about that as well. Is do you take only selected few, or you take all of them? And since we work a lot with the regulated industry, it makes sense to take all of them, because we want our clients to deploy machine learning at scale. I mean, so not like 1 or 2 proof of concepts, hundreds of machine learning models for each plan. And this is, in my opinion, around the corner, that type of deployment, where you just have digital clones for your entire plant. Wherever you have something moving, I mean, you have some, analog digital clone for that. There's nothing that's holding it back. Yeah, go ahead.
So then if you want to run a query for a specific device and a small subset of sensors, are you querying for all the sensor data, or can you query for just the sensors you care about?
No, for example, here you're basically querying for the physical equipment, and these are basically all the sensors that sit on the physical equipment.
Okay, so you say when you query basically the digital twin, and you get all the data for the time period you selected.
Correct.
Okay, gotcha. Thank you.
But the idea is, of course, when we do a project like that, that we provide all the data, so we don't have these projects where they always start with, okay, first we need to bring the data over before we can actually model the data or create a data like an analytical model for it. It would be too time consuming, especially for the regulated industry, because then you have to do validation on the data that you're bringing over. So every time, I mean, you change something, it has to be revalidated, and this is of course very costly.
Okay, thank you.
Okay, let me just go to the next slide. Yeah, so here's some feedback for QuestDB. So first things first, I mean, it's really fun to work with this database. I mean, I like the fact that you just spin up a Docker container, you have your web interface, and you get going within like a couple of minutes. Very, very nice. I also think the choice to have different protocols for writing and reading is also a winner. I mean, we found out that we can push a lot of information through the influx line protocol, and having a Postgres adapter makes it also so much easier to write software that actually reads the data from it. I mean, as you see, we can display the data in Grafana and have no problem. So the strengths, of course, for the database is that speed and the small footprint. I think this is a little bit overlooked these days, but I think it will become very, very important very, very quickly. We already had, people that talked about the cost of their cloud infrastructure, because everything costs money. I mean, to make a database that's fast, but needs like 50 cores. I mean, yeah, that is fast on paper, but I mean, if you have to start paying for it, I mean, then of course, you have to basically also take that into consideration. So the place for the database in manufacturing is that we see is definitely on the edge, where you need a very fast database, to do edge computing, and also as a hot database or cold data store in the cloud. That's my personal opinion. There are a lot of time series databases out there, and also very, very good one. But I think schema is very important. I mean, for me, I like to basically have the ability to create new schemas, for, as I mentioned, complex data types for machine learning or online monitoring. That is really a plus for me. Then also the fine tuning for out of order and commit lag is very important, because we have different data streams and we have also different update rates. So this is also something that's important for manufacturing. So my wish list is, of course, I would love to see, and I think you guys will talk about that a little bit later. Something automatically to tune the database. So I don't know all the different knobs you can turn, to increase performance. So that would be something that would be handy. Postgres has something like PG tune, where you can just put in some parameters and gives you a good configuration. Data update, somebody was talking about that. Updating the data is, of course, an important feature for us. And then the other one is, that I still think would be really great. It doesn't have to be maybe QuestDB, but somebody as ML-specific features, So, for example, to get matrix and tensors, aligned matrix and tensor data right from the database. So you basically just like a very fast internal query that basically prepackages the data before they send them to you. I think, yes, you can do that with SQL queries, but, maybe there's something, in the database world that also would make that a little bit faster and easier. And of course, there are tons of applications that would benefit from features like that. Thank you. That's the end of it. So thank you, Pei, for setting out all that up. Damien O'Connor will also work with me, to get the presentation up and running and create this type of proof of concept. Emmeline is our marketing person, and she does a great job basically styling all our presentation and blogging them on, putting our blogs on LinkedIn. And if you have questions or inquiries, you can talk to Eileen or myself. That's it.
Thanks a lot. Thanks, Holger. It was a pretty nice presentation. I learned so much. And I think regarding your wish list, I maybe later Flat will have time and he can totally respond to that. Or Flat, you want to talk about that already right now regarding what he wished for?
Yeah. Well, the updates, we're kind of acutely aware the updates are coming. Updates are kind of important and they're coming. We're working on them quite as we speak, in fact. So Pei mentioned at the beginning that we releasing version 6.3 very soon, hopefully a couple of weeks, and this would have updates. So that's the exciting bit. Yeah, regarding the TensorFlow and matrix calculations, we are kind of doing proof of concept here with Python. Hopefully that would answer kind of all your guys' prayers. So the idea is that you should be able to construct pandas data frame directly from the data in the database, so without sending data on the wire. and then you can take it away in Python. Use Python libraries, entire suite of Python infrastructure, pretty much. So that's
Vlad, that sounds fantastic. Could you just take us one step deeper into that?
Okay. So basically, what we're trying to do is we are trying to align our storage types for all the types that we support with types that Python, with storage types that Python has, right? The idea is that we effectively we run a VM inside the database, like a much like Docker VM. So this Docker VM, it's a proper VM. It's not interpreted language. It's a VM, pretty much like operating system VM. So which can be installed with like a Python libraries, anything and everything that you want. Then what happens is, over the network, you send Python code to this VM. This Python code executed, basically what it does, it bridges, it accesses data directly on the machine by memory mapping the vectors that we store already into Pandas data frame. So it's a kind of lazy mapping. We just allocate kind of we map effectively virtual memory to disk, right, and hand over address pointers to Pandas data frame. And then you effectively have data frame on which you can run whatever Pandas infrastructure kind of you need. So we provide the continuity of the data, so the Pandas can basically treat the data as a contiguous kind of piece. And because it's a VM, so you can load whatever libraries are installed in this VM. So you can use, if you want, all of the hardware that's available, like kind of GPUs and whatever else. So it's basically, it's just fully fledged Python infrastructure.
It sounds excellent. Have you tested it with other high performance libraries like Number or any other vectorized?
Yeah, so we do support right now kind of more primitive types. We don't support like strings yet, symbols, this kind of things, but we support numeric types like doubles, longs, ins, that kind of stuff. And it's basically, it just works well with anything. So it really is like for a library, Python library, it has no ability to tell that's QuestDB behind it. It's okay. Basically, it's just the memory it accesses, right? So we remove all of the QuestDB links or anything like that from there. So any library works with Pandas data frame.
Final question from me. Thank you very much. Do you have any, or have you used or tested any dynamic programming with it? So where you're getting a time series which is being continuously incremented, and rather than recalculating a sliding time series function over the entire input set, you're only recomputing the additional data to generate your sliding window functions?
No, we haven't tested that yet. No.
Okay.
Okay. But yeah, no, I wouldn't lie. So we haven't tested it yet, but that would be ideal if we could kind of create sliding windows over the data. I just kind of off the top of my head, I don't even know how that works in Python yet. So we're gonna need to do a bit of a research.
Not very well.
Well, in terms of kind of, we're interested in mechanics, basically. What does it do under the covers to provide sliding window, so we can facilitate it from our side.
Thank you so much.
No worries.
Vlad, just piggybacking on what Orin is mentioning, is there any estimated time when the Python thing may arrive?
No. Oh. There isn't. I'd like to give you I'd like to basically like just a bit of an insight into how we work. So we focused on QuestDB stability and little bugs that kind of come here and there. So just to make sure kind of existing users with whatever existing functionality they employ happy, so that, and it's kind of as frictionless as possible. and we're trying to kind of gradually slide into more strategic items, and one of them is this. But we did do, as I said, we did do proof of concept with non-string types. We're gonna kind of delve into remaining types. I would estimate maybe in a week or so. So we're gonna be in a position where we understand basically where we stand. Yeah, we'll try to get you updated on the Slack channel and somehow else on our progress. We don't do it enough, but we will. So we do R&D work in the background on this kind of pretty much continuously. So
okay, and regarding like the rolling windows or sliding windows, I'm guessing that's something that when the Python kind of idea arrives, if in the future, then that's something that we'll be able to use straight from there. So you're not thinking about implementing it separately somewhere, because many people have asked for it. So that's why.
Yeah, so that's right. So if we can have Python do it well enough, so that would be our preference. Yeah, so we definitely well, I kind of will probably speak for myself here, but I acknowledge the limitation of SQL language, and we're probably not gonna basically conquer the world with SQL in this regard. So things that we can do via Python, that's our preferred route for everything kind of calculation intensive.
Okay, thank you.
Cool. So yeah, thanks a lot for all the questions. And I think we know like the second part of the meetup, we have a topic regarding the InfluxDB protocol and the performance tuning for that. So yeah, I'm gonna hand it over to Andre for that then.
Thanks, Pai. Let me share my screen. Okay, you should see the slides.
Yeah.
Good. Okay, good. So yeah, my name is Andre. I work at QuestDB core team as well as cloud team. And today we will be talking on InfluxLine protocol, some kind of guidelines for performance tuning and all of that. So let's start with a quick recap of the protocol itself. So as the name suggested, it was first used and implemented in InfluxDB. But since the protocol itself is quite convenient, it's not only Influx database which uses it, but also QuestDB. So at QuestDB, we use it for high throughput data ingestion, and that's the usual way to go when you want to have really high numbers in terms of throughput. And unlike InfluxDB, we implemented over different transport protocols. So Influx supports it over HTTP. In our case, we support lower level protocols like TCP and UDP. So this means that you would not be able to use Influx specific client library to ingest ILP data, but the protocol is simple enough, so it's quite trivial to implement a client. And we also we have implemented clients for some languages like Java, and we also have a C++ client in progress. It should be available soon, I think. Yeah, as for the protocol itself, it's quite simple. It's text-based. It's somehow similar to CSV in terms of formatting the data. And yeah, it consists basically of the 4 parts. So the table name, then the symbol set, all of your symbol columns, then the column set, all of the remaining columns along with their values, so key value pairs, And the fourth part is optional. That's timestamp. Yeah, so speaking of ILP, we do not have explicit transactions in ILP, but instead it implements implicit transactions. So we have three strategies when we commit the data, when the data gets committed. All of that is, by the way, documented. Recently, we have updated the documentation page. All of the ILP related sections are now, I think, much better than they used to be. So they are quite comprehensive. So don't hesitate, just check out the documentation. If you struggle with something, it should help. So the first strategy is row-based. Basically, when you reach a number of uncommitted rows, the database commits them, all of them. Then idle table timeout. So if you do not write anything for a certain threshold, your data gets committed. And the third strategy is interval based. So if your data ingestion is not really intensive, so you're writing like a few rows, but you keep writing them, in that case, idle table timeout does not kick in, but instead interval-based commit happens periodically. And once again, all of these strategies, they are documented in a good level of detail. So speaking of the implicit transactions, the motivation here is to have as less frequent commits as possible, because this way ILP protocol shows better throughput. So it's like the motivation is performance. Now we also use, speaking of terminology, we use definition of out of order data. So your data, your sample data, in terms of your application logic, may be ordered. You may get you may get your data for a fixed interval, let's say so. But when you write the data, it may be delayed because of different reasons. It may be written in different order. And that's what we call out of order writes or out of order data. Obviously, since QuestDB is a time series database, we want the data to be ordered in terms of time. So like when committing the data, the database would need to sort your rows to append them to column files properly and make them available in queries. So out of order writes, they have one important rule to keep in mind. So you need to use a partition table to be able to write data out of order. Otherwise, you just get an error back from the database when you try to insert a stale record into the database. So just keep that in mind. Now, the next term that we're using in QuestDB is commit lag. So the commit lag is an optimization that we have in the database. And the overall idea is that it should be set to the value where you expect the data to arrive with a lag. So if you expect that your data may arrive with a, say, 10 seconds lag from the real time, so the out of order lag, your expectation of it is 10 seconds, just set your commit lag to 10 seconds and that's it. And when a commit of out of order data happens, the database just sorts uncommitted rows that are older than the lag value. So if you set your commit lag to 10 seconds, your last 10 seconds of data would not be committed when a commit happens. So that's like a blind window. But when the next commit happens in, say, 10 seconds, that window moves pretty much. And once again, the idea here is to be able to catch up out of order writes and write them on disk in one go. So commit lag is just optimization technique that we use in the database. And when you try to configure a commit lag, you should not use a very large value for the lag. So it's fine to have outlier values periodically written. So by outliers, I mean rows that are older than the commit lag. It's fine to have them periodically, as long as most of the out of order writes fit into the commit lag value. And to illustrate that, let's see the following picture. So here we have your sample time. So timestamps that are used in your data. And on the x-axis, we have physical time. And ideally, they should match, but yeah, it usually doesn't happen. And the data points arrive at different times, physical time, and the timestamps also may like go in time forward and backwards. So your data may be out of order, and here the data is out of order. Sorry,
Andre, can I just add some color to this? I'm sorry. So just kind of, we thought it'd be kind of easy to think about commit lag as a clock skew, right? So if you have multiple sources publishing data in, each of the sources use their own clock, right? And as you can imagine, as data arrives to central location, these clocks do not necessarily agree. There's slight skew. There's one clock is forward, one backwards. And from viewpoint of database in a central place, these timestamps look like Andre illustrated here. So it's those dots that you see effectively clocks of the sending devices.
Yeah, so clock skew may be one of the reasons for non-monotonic timestamps, right?
Yeah, but
also,
there's
sorry.
There are lots of other reasons why you would get data coming in from times that aren't just now. I mean, we run into it all the time, and we actually had to make our commit lag 1 year in order to make our database work without the hard drive space blowing up to 1000x of where it should be. And then, so this has been a kind of a pain point for us. Like, data can come in historically at any time and be out of order. That's just like a very, very highly standard thing for APIs and databases and time series, especially in IoT, financial data, or really anything if you're resyncing data or whatever. So we're a little bit confused about what to do with commit lag in that scenario.
Yeah, so let me take this real quick. So the commit lag, as Andre mentioned on the previous slide, is optimization setting, right? So it's the value of commit lag should ideally not be set to a year. It's too much, and it should be set to a reasonable clock skew you expect from publishing devices, right? And if the values, if for some reason, say let's say you set commit lag to, for sake of argument, 5 seconds, because this is how much your kind of clocks could be out by. If you do receive data that's wildly outside of this, like you receive data kind of with yesterday's timestamp, it's fine. It's just not going to be as optimal to insert out of order as with commit lag, but it will go in.
But what we found is that the database would basically explode to sizes that were like 100 times the hard drive space without it, and it wouldn't recover or reclaim that space.
It depends on the version you're using. To be honest, we did have we have a notion of kind of garbage collection in the database. So just to understand the out of order insert is effectively copy on write for a given partition, right? So one way to minimize space use is kind of have partitions kind of reasonably sized. Like, for example, single partition should probably be no more than, I don't know, 20 million, 50 million rows, that kind of stuff. So the idea is when you update partitions out of order, we do copy entire partition with data changed. And the old partition is garbage collected in the sense that we keep track of queries looking at the old data, and as soon as queries stop looking at the old data, we remove old partitions. We did have issues with this garbage collection mechanism where the logic there was flawed and it could leave partitions behind. It was possible, but this is which is why I think this 6.6.2.1 is where we polish this garbage collection to.
Okay, yeah, I mean, I think this was on 6.2.0 and we just moved to 6.2.1, so we can reduce our commit lag, try again and see if it, and you're saying garbage collection of hard drive files, not memory, right?
Hard drive files, yeah.
Got it, okay.
So
okay.
we basically evaluate all the partitions that are kind of latest. We check all the partitions that are not being used by readers, and we actively delete them.
That's exactly this sounds like the issue we saw. Is we saw a bunch of empty partition files and not being cleaned up. Okay, thank you.
Cool, no worries.
Yeah, anyway, if you encounter any issues, like just create a GitHub issue or just write on Slack. We'll be happy to help. And
there's a rule of thumb, like it's I can't really overemphasize that commit lag is really should be set to around the clock skew of publishing devices, right? So if any of you guys kind of having to overcome any issues with the massive commit lag, let's discuss this and see what can we do to to mitigate it.
Yeah, 1 year of commit lag sounds like too much. So anyway, let's return to this picture. Here we have this commit lag set for 10 minutes, and most of the records fall into this interval. While it's okay to have occasional outliers. So occasionally here we have like records which have stale timestamps and they fall out of the commit lag. In this case, yes, we will have a partition rewrite, but that's fine. It should not impact the performance that much. So yeah, commit lag is an optimization, and it's quite important to understand how it works and how to configure it properly. So as for the configuration of out of order, we have two global settings. The first one is commit lag, the default value, and as well as the number of maximum uncommitted rows. So these two settings are used whenever you create a new table. If you do not specify them explicitly, like here, we use global settings instead, and each of the created table gets whatever was the default at the creation time. Later on, if you want to change any of these parameters, you can do it as well for any of your tables. So once again, out of order writes, the whole idea behind transactions in ILP, the whole idea behind them is to have less frequent commits, also to accumulate most of the out of order writes into the commit lag and write them in one go. As for the commit lag and the maximum number of uncommitted rows, if you do not know which values you should use, just use default settings and experiment, measure the performance, and later on, if needed, fine-tune them. So we suggest to start with the defaults. And obviously, if you have a way to maybe pre-sort your data before ingesting it, that's also nice. So in-order data is the best possible scenario, but it's totally fine to have out-of-order writes, because having in-order data all of the time is just maybe impossible. So let's go over the threading model that we have in the database when it comes to ILPs. Here on this diagram, we have a couple of client applications. Each of them writes ILP messages through its own TCP socket. And the data is handled by worker threads, IO worker threads. We have a so-called IO worker pool, which is a thread pool. So each of these threads handles one or more TCP connections, reads the ILP messages, parses them, validates them, and later on it sends the records to one or another writer thread. So we also have another thread pool in the database, which is called writer pool. Each writer thread is responsible for all of writes for at least a single table, but obviously if you write into more than, in this case, 2 tables, each of the writers will be responsible for a group of tables. As for the writers themselves, we have the single writer architecture. So for a particular table, all of the writes will be handled by one or another thread. And the thread will be a single one, simultaneously. Each of the writer threads, if your data is out of order, it may send the data to the shared worker pool. Shared worker threads, they sort out of order records. So we parallelize sorts pretty much to improve the performance here. And when the data is sorted, it gets written to disk. It gets appended to the column files. So that's the threading model that we have. It's kind of a pipeline. Yeah, so let's move on. As
Andre,
for
sorry to interrupt you, Andre. I'm just very conscious of the time, as we already run out after the hour. How many more slides do you have?
A few of them. Okay. I will speed up.
Okay. Or perhaps we could leave just five minutes for people to ask questions. I don't know. I think quite a few of you probably have to go. So yeah.
I think Grant wanted to ask something.
Okay.
Yeah, in this, so if you don't have, if you're getting a bunch of out of order stuff submitted, the writers are going to write it to disk. Does it then get taken and like, is there some background job that then is going to resort the disk as things are coming in later, and that's the performance hit? Or is it just not going to get resorted on disk, and then so each time it's doing a read, it's got to sort through the disk and find it?
Nope. On disk, data is always sorted in terms of the designated timestamp. So we make sure to sort it before writing to disk. So queries readers do not need to sort the data.
Yeah, we penalize writes pretty much. If there's a big chunk of data out of order, it would. This is where the shared workers come in. So we try and kind of leverage multiple threads to do merge faster.
Okay, so it's just a performance hit on, it has to do some sorting. That's really the only expense is what it comes down to.
That's right. Yeah. So only
Okay.
ingest. So from that point on.
Yeah, that's correct.
Thank you.
Cool. More slides.
Okay, let's move on really quickly. So as for sizing guidelines for the worker pools, we do not recommend you to over provision worker pools. So you should keep them in total size, less or equal, but better less than the number of your CPU cores. And you should also leave a few cores available. So the number should be slightly less, like, I don't know, it depends on the concrete machine, but having a pair of spare cores is always a good idea. So yeah, JVM and OS processes may be running there. So another sizing guideline for speaking of ILP, if you're writing into multiple tables from multiple TCP connections, you may want to configure more than one writer thread. We have a single one by default. And 1-to-1 ratio between writers and tables is ideal in this scenario. If it's not an option, you should not write to all tables from each connection. Instead, you should just try to group connections in tables and have them separated. And if you're writing into multiple tables from a single TCP connection, a single writer thread should be more than enough for handling all of the writes. And the third group of guidelines is that you should reuse TCP connections as much as possible. So keep them around, avoid opening and closing them frequently. And ideally, the ratio for TCP connections to IO workers is 1-to-1. And we really recommend you to try to keep this ratio. So avoiding to under or over provisioning TCP connections. Yeah. So worker pool sizes, they're kind of documented properly, but just keep in mind that you may set the properties explicitly. If you do not set them, the database, the database chooses one or another value based on the number of available CPU cores. Check documentation to find out the logic. As an example that we have, so on AWS, more or less medium-sized machine, virtual machine, C5 9x large with GP3 BS volume and X4 file system. You can go as high as around 1 million rows per second in TSBS with one table. And this means that the data ingestion scales pretty much. So with one table, you get 1 million rows per second. This means that you may write to 10 tables, 100K rows per second per each. So you may use this scalability principle when you when you want to fine-tune your configuration and your hardware. And as for client size, really quickly, once again, if there is a ILP client library available for a language like Java, maybe C, C++, just use it. If you use your own library, you wrote it, try to avoid writing to socket row by row, write in batches. Otherwise, you will be you will see some kind of penalty and overhead of system calls. And as for batch sizes, it depends on several factors, but something around a few thousand rows per batch is not a bad choice. And the final thing I wanted to discuss is memory footprint. When it comes to ILP, if you write to a large number of tables, like hundreds of tables, consider decreasing the append page size that we use in writers. That's because the default value is 16 megabyte. And this means that for each of the table you write into, we also allocate a couple of additional buffers for out of order writes. So the memory overhead per each table is 32 megabytes.
It's per column, Andre, per column.
Sorry, yeah, per column. Yeah, forgot to mention that. So yeah, it depends not only on the number of tables, but also on the number of columns. You may use a single table with a lot of columns, and the rule applies there as well. And that's pretty much it. Thanks a lot.
Thank you. Thank you, Andre.
Right.
Yeah, so like anyone has questions regarding the topic or any other questions? Cool.
Sorry, do you hear me?
Yeah.
Yes.
Yeah.
Hello, thank you to Andrew for all the information. I'm not sure, but I believe that all this information is not in the documentation already. I'm wrong? Because I think it's very interesting to have this in the documentation.
In fact, I was mostly using documentation when preparing these slides, except for maybe one picture.
Jose, what Andre said in the beginning, maybe kind of there's a lot being said. It's kind of hard to remember all of it. We redone our ILP documentation recently, literally in the last week or so. So we found that it was confusing, basically same thing in multiple places, and these places don't even agree with each other. Now it's kind of was pretty bad to understand what the LP does, and we went on the limb here and kind of consolidated documentation in one place. That is very recent. I just want to stress it. Basically, if you saw documentation a month ago, you are totally right. It was shit. So now is very good.
Okay, thank you very much.
We agree with Jose, and really glad to hear that it's we're consolidated now. That's fantastic.
Cool.
And if you feel that it's still not top notch, and it could still be improved because there's a lot of information, and yeah, it might not be super easy to find, let us know. You know, it's a process. We try to refine it as we go. So don't hesitate to tell us in the future as well.
Sure, I will say something in Slack.
Yeah, it's really helpful to have like the suggestions you guys had about like, oh, commit lag should be kind of intuitively this range, it should be small, things like that. If you add it to documentation, like, oh, per TCP connection, the ratios, you shouldn't exceed these bounds of ratios, things like that are really helpful, because then you don't really know when you change something, that if it's like per column, and you change it from 16 to 32 megabytes, that you're actually really maybe multiplying your RAM huge. And like, that's not intuitive from the documentation prior. Maybe it is now, but stuff like that's really helpful, is just like to give you kind of more intuitive feel for what these parameters have an effect on when you're changing them in the database.
Yeah, very cool. We'll go through these slides ourselves one more time and just check if everything that's valuable in the slides is also in the doc, just to make sure. We'll do that.
Great. I remember, Holger, you say you also have questions regarding the InfluxDB Live protocol, right? I don't know. After this, is it helpful?
Yeah, after this, yeah, that was very, very helpful. That was excellent presentation. Thank you so much. I mean, that helped a lot.
Cool. Hope that I already answered your question, but if not, then you can also ask now or later in the community Slack. Yeah.
Yeah, and just from one kind of nugget of information, we discussed this out of order and partitions growing and stuff. I think in 6.2 or maybe 2.1, we introduced like a SQL command to vacuum partitions. So if our kind of garbage collection does not work still, there's a SQL command to purge partitions. It just to put it on your radar.
Cool. Any other questions?
Thanks for the presentation. Yes, sorry. Yeah, thanks for the presentation. It was really helpful. I was trying to, I'm new to QuestDB, and I'm sorry that I'm mentioning the competition, so TimescaleDB. I was trying to see how I can compare these two. So I thought, let's look at the benchmarks. Let's try to come up with a new benchmark to see how we can compare these two. What I did was to use the case. I don't know if you know K6. K6 is a performance testing tool. So I used the XK6 SQL extension, and you basically enlightened me with your presentation by saying that the number of TCP connections doesn't necessarily help with the number of writes and stuff. So I try to like create hundreds of virtual users, and each virtual user were using basically hundreds of connections. So yeah, it would be tens of thousands of connections against the database, and I was getting a lot of these error messages, which you also mentioned in the FAQ about insert failures and stuff. But my question is, would PG Bouncer help with this? Or should I change how I test the database?
Yeah, in general, I would suggest keeping the number of PG wire connections. I guess that's what you're using, to keep them smaller.
Mm-hmm.
So it's kind of, it may sound counterintuitive, but usually you benefit from keeping the connection pool smaller rather than larger. And hundreds of connections sounds like too much to me. So you may run into a lot of problems. I don't think you will see good throughput, good performance when using it. So yeah, as for PG Bouncer, I don't think we tested it ourselves, did we? Integration with PG Bouncer.
I've seen someone sent a message into the issues in QuestDB and somebody answers it. It was about TLS, but somebody mentioned PG Bouncer. So
we are using PG Bouncer for cloud thing, for cloud infrastructure. We should be able to support it, but we're gonna have to come back to you on this. And I just wanted to also add, we spoke about ILP here. So for QuestDB, ILP is well, for now is a flagship in terms of performance protocol. So PG wire generally is a compatibility protocol. I would not recommend ingesting data over PGWire overly aggressively.
Oh, thank you. Thank you.
Cool. Great. If there are no more questions, I mean, there might be more, but if there are no more questions, I think it's been a long session today, and I want to thank everyone for participating in, and also as a reminder that if you don't know that we have Slack community, you can find our Slack channel on the website under the community section. So you can ask questions there, and our engineers are all there to help. On the other hand, we also have a newsletter. It's a bit harder to find, but it's under the community on the Swag page. For now, we're gonna make it more visible. But if you want to get updates of our product, you can also sign up a newsletter. Yeah, but that's about it. Thanks a lot, everyone. So we're gonna call it an end here and see you next time.
Absolutely.
Yeah.
We'll see you next time. Thank you very much, guys.
Yeah. Thank you.
Thank you.
Bye-bye.
Thanks a lot.
Thanks,
you.
everyone.
Bye.
Bye.
You.